Good enough. All right, cool. So, yeah, basically this is an intro session for like ML and stuff. I'm gonna be going over like MLPs, so just like the basic building block of all of machine learning. How do you optimize that? But that starts at like linear regression, so I'll go over that a little bit. And hopefully you can get into some more advanced stuff like CNNs and RNNs. It's not going to be thorough. It's definitely not going to be thorough. This is like 1 hour and a half, so don't expect to be super thorough, but hopefully it gives you like a good understanding of things. We want to talk about this paper next time, which is the basis of all models actually. I can say that now, and it basically is. If you look at any model, it has attention in it, so this thing right here. But if you don't know optimization or like RNNs, it's kind of hard to talk about it. So we wanted to kind of have this session to go over some of the basics. So cool. And if y'all already know some of the basics, you might find this a little boring, but there's food, so hopefully that helps. So anyways, we'll start with the basic like linear regression model and kind of build up some intuition from there. So the idea behind any machine learning model is I basically have a set of data and I want to model that data somehow. So I have a set of data, maybe that's, I don't know, some variable. Maybe we have like house size or something, and we want to see what the price of that is. It's the good old house example. So we have X, our input data, which is just our independent variable, and then Y, our dependent variable. So X is maybe that's house price, and Y is, this would be house size, and Y would be like the price or something like that. So we kind of want to model this. And you have some data points here with some arbitrary values like this, perhaps. Maybe it doesn't look like that, maybe it does, but in this case, let's say it looks like this. And an easy way to model this is to, well, just draw a line. So linear regression is just, we have some data, and we're gonna draw a line straight through it as the name implies, linear regression. So the idea for any machine learning model is we have some input here, and we just want to predict an output. So this input can span multiple different variables, and if we increase the number of variables, it's going to make our space a lot larger. I'll talk about that later, but in this simple example, with just one variable, we basically just want to model this using a line. And to do that, we would say, I don't know, maybe we have a model, y hat, and by model, I mean some way to draw this line. So we have some model, some way to model, or some way to hopefully make predictions on this data, and this will be given by some parameter which we will optimize, and we'll talk about optimization later. But basically, find a line that models the data best, and we'll talk about what best means later as well. So we'll say y hat is equal to, so this is going to be a prediction, and this will be, say, w times x, and maybe plus b. Bias isn't a big deal. And basically, this is just the slope of the line. So if it goes through 0, we basically have this line, and we want it to model the data well. And by model it well, like if I give it some house size, maybe this is, I don't know, some square feet, I want it to give me an accurate prediction of the y value. I mean, obviously, if I draw a line like this, it's not a good line. But if I draw one like this, it's a much better line. So that's the idea behind like basic machine learning with one variable. So we can increase the number of variables, and we would draw a plane through this data. So just to kind of show what that would look like, we would have two variables, maybe x1, x2. So maybe this is like size, house size, and this here is, I don't know, number of bedrooms. Maybe they're correlated. I'm not going to worry about correlation here. So two variables, and I need to draw this kind of 3D-ish. So two variables, and then we'll still model the price. So now you get this three-dimensional space where two dimensions are you have two dimensions as your input, and you have one dimension as your output. And let me draw this a little differently, like that. x1, x2, and y. So you have some data in this three-dimensional space, and you're going to draw kind of this plane here. I don't know if it would be hard to kind of visualize. But basically, you're drawing a plane through here instead of just a line. And you have two variables, and you can increase this to however many variables you want, and it becomes impossible to see. But the idea is the same. You have a bunch of data. You have a bunch of data that has values. Basically, it takes on, like, in this case, it would be the number of bedrooms and a size, and you want to predict the price based off that. So you can increase this. Maybe you have number of bathrooms and stuff like that. So then you get a four-dimensional space and so on. And you just want to create this function that models the space well. That basically, given some set of inputs, so if I give it, say, one bedroom and, I don't know, size of 2,500 arbitrary units, it would give me an accurate price, say, $100,000 or something like that.
So each input attribute is a new dimension.
Yeah, I mean, you can add, so however many variables you have, it's a new dimension. So if I have 4 variables, it would be a 3-dimensional space. Or if I had 3 variables, so x1, x2, and x3, it would be a 4-dimensional space, which you can't really visualize. But it would be 3 dimensions of your variables, and then 1 dimension for your the variable you want to predict. Yeah. So there would be 3 dimensions, and then you have some other dimensions. If you can't visualize it at this point, it becomes impossible. So it's easiest to visualize it using just like using 2 dimensions, input, output. But you can abstract this to higher dimensions using the same equation. So like the way we showed here, like y hat is equal to wx is the simplest way. So we have this data here. And basically what we can do is we can say, oh, well, we need to draw, the simplest idea is just to draw a line through that. And do that, you can do wx equals, or y hat, so our model's prediction is equal to wx plus b. So this here is just saying we have a line, and we can move it up and down via b. So that would be kind of our bias here. That's what b is called, the bias. It kind of shifts the line up and down. And you also have w, which is just the slope. So that just kind of tilts the line up and down. Normal calculus, normal old equation, you just have w. And in this case, maybe w is equal to like 5, and b is equal to, I don't know, 1 or something like that. And to make a prediction, assuming we have this really good fitted model, we want a prediction on the price. Maybe this is actually like 5,000, 50,000. That would be more accurate, and this is like 10,000. To make a prediction, we would then feed in some variables in there, and we would get out an output. So in this case, since we're just modeling house size versus price, we would say our predicted house price, maybe given a house size of, I don't know, 10 arbitrary units, 10 square feet, that's what we'll say, plus 10,000. We just feed it into this equation here via x. So like this is our model here. We know what w is. We trained a model to get w, which I'll go over how to train this in a sec, but assume we have a good fitted model with these parameters here. We then put 10 into the model, and we need to get out an output, which is going to be the prediction of the model. And this would be whatever that is, 500,000 plus 10,000, so 510,000. That's the prediction here. And I mentioned that these are parameters, and this is a variable. So the parameters are what we're trying to optimize. We have several parameters, which is what we want to tune. This is what we want to change in order to make a better model. So a better model has parameters that give you a better output prediction given an input. So x is our input, w and b are our parameters, the stuff we're trying to optimize, and y is just our output, which we're trying to model given an x. So we can add a bunch of w and a bunch of b, which is what gives you a neural network, basically. So this is the one-dimensional case. So y hat is equal to wx plus b is the one-dimensional case. We can abstract this to multiple dimensions. So let's say x is a vector. So in the one-dimensional case, this would be a vector of size 1, so it's just a scalar. And w, in this case, would be a 1-by-1 matrix. So w is going to be a matrix. In this case, it's also a scalar in the one-dimensional case. And b is going to be a scalar as well, so scalar, because y hat is a scalar, so y is also a scalar. So everything's a scalar in the one-dimensional case. It makes things really easy. Now let's say x is going to be in 2 dimensions. So like we said up here, x1, x2, like here, it'll be a vector of size 2, where the first slot, or where the first value is maybe price, and this, or the first value is the square foot, and the second value is maybe number of bedrooms or something like that. So we increase the number of parameters, but now the shapes don't work out. So we need to increase W. So W is then increased to a 2x1 matrix, which is drawing this plane here. So you have 2 values, you have 2 inputs that you're modeling and 1 output. B is also going to be 2. So what this looks like is it'll be a inner product between W and X. So all you're doing is you're doing, say, let's say W is equal to W1 and W2. Then all you're doing is an inner product on W and X. So this part here is just going to be our parameter W, W1 times our first value X1, plus W2 times X2. And then plus the bias. Actually, this would be 1 value plus the bias. So I'm going to just get rid of the bias because it's really annoying and you don't really need it. You only need it whenever you have a small amount of parameters. So I'm just going to get rid of it because it's really annoying. But you can always add a bias here and it takes the same shape as the output shape. So yeah, and we can add as many variables as you want. And every time you add a variable, you add another W. So we add another variable. If we add, say, X3, we would have W3. And this becomes more, I don't know, you have another variable there. So this is just normal linear regression. So now the idea is we want to optimize this model so that it fits the data well. Right now we just have a model, and I said assume we have a good model, and a good model means you have some W that basically moves this curve or plane in the space such that you get a good output. But I haven't mentioned how do you do that. So how do we do that? The idea is, let's say we have this space here, so our 2-dimensional space. This is X, this is Y. We want to model Y, and we have our inputs X. Oh, cool. Yeah, so we have some points here, and we're drawing a line. So the idea is if we have some model that we're trying to optimize, which is going to be represented by our line because a model is just some curve in some space. This is going to be our y hat equals, or I guess f function. We have this line here, and we want to optimize it. So at any point here, these are our data points. We have 4 data points here. So we basically have a data set, and we want to optimize this line according to the data set. And the idea is we can look at the residuals. So if we look at this data point here, and we look at the model's prediction here, we look at the y values here, given this specific x value. So this is our x value that we're looking at, and this is the y value at that x value. And this is the predicted y value at that x value. So what we can do is we can look at the residual here, and the residual is just equal to y minus y hat. So this basically tells you how far is your model off from the input data, y. And we square that so that we get the, so that we don't worry about the magnitude. So if the data point was actually right here, it would be the same value because magnitude-wise. So basically all you're doing is you're saying, I know what my model predicted, which is this, and I want to see how far is it off from this data point. And you do that for every single data point. So if we call this, say, y1, and we call this like x1, y1, and we call this one here x2, y2. So we label all the points with some index, x1, y1, x2, y2, x3, y3, and x4, y4. You can basically get a residual for every data point here. So we would have a residual, maybe this will be R1 here, this will be R2, this will be R3, and this will be R4, where every residual R sub I is equal to the square of the of what our model predicted, or the square of the difference between what our model predicted and what the actual prediction was. So y hat minus y squared. And it doesn't matter what order you put it in, you can flip y hat and y and it'll be fine. So what this is equal to is this is equal to, if we swap out y hat with our model, this would be wx minus y squared. I'm removing the b because the b is annoying to deal with again. So these are the residuals here. This is Ri, and they should also be indexed here. There. All right, cool. So the goal is a good model is one that has the minimal residuals, or one that minimizes the residuals. That's just by definition how we're going to define good model, and in general, that's how you define it. So the way we optimize a model is we want to minimize these residuals. So the way you do that is by defining a loss function or a cost function or whatever you want to call it, loss or cost. And let's define this as the average residual. So this is going to be called the mean squared error, and you'll see why in a second. So let's see n. So n is equal to 4 in this case, is equal to the number of data points we have. And we're going to take the sum of the residuals. So I is equal 1 to n of our model prediction for some given input, say xi. Yeah, this would be f. We'll call that y hat I. Minus y I squared. So this is just the sum of the squared, or yeah, this is the sum of the squared errors, and this is just mean. So mean squared error. There we go. MSE. So you've probably heard of mean squared error before. If you haven't, this is what it is. It's pretty simple. And the goal is to minimize this. So we want to minimize the parameters in our model. So we want to find the parameters in our model that minimize L. So minimize the loss function. And basically a higher residual says the model is further off from the data. So remember, the residual looks like this. If we had a model that say had a line that looks like this, the residual would be further off, not looking at this part over here. So we basically want to find a model that minimizes that residual. And we do that, we take the average over all data. Yeah.
Is the residual like a mathematical term?
Yeah, I think it is. Yeah. So residual will be this. I mean, and it depends on the scenario. Residual can mean things in certain scenarios. They usually mean, yeah. In this case, this is how you define a residual in a machine learning sense. But machine learning tends to steal things from math, and
Yeah, that means all right.
yeah. Well, it kind of it's yeah.
Like when you get like R squared and R evaluated.
No,
That's
that's
a different thing.
yeah.
Never mind.
Yeah, this kind of uses statistics. It like kind of uses everything, machine learning. Yeah, the R squared is different, but we won't worry about R squared because R squared tells you how good a line is, and a line can't do anything whenever you have not aligned data. Not whenever it's if it's not linear, then you can't do anything. So basically, the idea is you want to minimize the loss, and you do that by changing W specifically. And remember, our model is y hat I'll start indexing it now, is equal to Wx, where x is some input vector. This is going to be a d-dimensional vector. This is going to be a d by dimensional matrix, and this is going to be a one-dimensional output. So this is the idea here. Minimize this given all data, or overall data, because we're averaging over all data here. So minimize the loss by changing W over all our input data X. You have this data, you want to find a line that basically has kind of the average or plane that basically minimizes all this error here. And that will fit a line that is what is defined as best. That's just how we're defining it. So to do that, you can do this in a closed form solution because it's linear. But I'm not going to go over how you do that. Like if you wanted to look it up, it's some equation. I'm forgetting it right now. Just if you're curious what the equation, do you remember the equation? Yeah, it's some mess. You take like the inverse and stuff. I don't want to derive it either. It's useless because if you only have a line, then you can get a closed form solution if you have a line, but if you don't have a line, then it's useless. So what we're going to be doing is something called gradient descent. And gradient descent is a way to basically slowly change a parameter or a set of parameters by just looking at the gradient of the loss. So the idea here is, in this simple case, is we have this loss function and we want to minimize the loss function. So to do that, you can probably think of calculus and be like, oh, I want to find the minimum. I want to find just the minimum of a function. And you can do that via calculus. So the idea is we have this parameter space here. So this will be W. This is a one-dimensional parameter space, and this is our loss. So given some W, some value of W, this is how we're going to visualize it. Given some value of W here, we get a unique, or we get a value of the loss. So maybe if we have a value of W that's like 1, it doesn't do too well because the line maybe looks like that. Like it's really, really low. Like it has a really high residual value for every single value. So we get a really, really high loss value here. But maybe if we have a W that's like, it tilts the line up a little more. I don't know, maybe this is 10,000 or something like that. The housing prices are high. Then we have a lower value for our loss, and we want to minimize this. So let's say we randomly initialize W, and we get a W that gives us a really high loss value. It probably will. We randomly initialize it. Let's say we have a value of like 10 or something for W. We pick a random value. So the idea is we can take the gradient, which I'll show in a sec. The idea is we can take the gradient of our loss function with respect to our parameter W, and what that'll do is it'll give us a direction pointing in the steepest ascent. Yeah. And the idea is we can flip this and we can perform gradient descent by continually finding the direction of steepest descent. So basically this right here represents dl over dw, which is the direction of steepest ascent. And we can take the negative of that, and it points in the direction of steepest descent at that particular point there. So for a particular value of w, which in this case is like 10, we find dl over dw at w is equal to 10, or the negative of that, and that points in this direction of steepest descent. Then what we do is we're going to kind of step in that direction a little bit, and that'll give us a slightly better value, or a slightly better model, because it lowers the value of L a little bit. And then we're going to say, okay, what is the derivative at this point? Which is going to be different from the derivative at this point. You can see it's slightly up more, so we have to reevaluate this derivative again. And we say, okay, I see the direction, I'm going to step in that direction again. And you keep on doing this over and over and over again for all your data, and eventually you will find a minimum here. Or hopefully you'll find a minimum. And if you keep on stepping in this direction, you'll get a vector that's like super small that isn't pointing anywhere, and you will have found a minimum. It may not be the optimum or the global optimum, but it is a minimum. You can get around finding the global optimum with optimizers, but the most basic optimizer is this. Now the way you do that is we want to optimize W, right? So we want to update W. So W is going to be equal to W, and we want to step in the direction of the negative gradient. So it'll be W minus dl over dw. And this is just what we did up here. We're saying we know what W is, we know what the direction of the gradient is, and we step in the negative direction of that. So that's all this is saying. That's what this equation is. And what you will see is you'll see an alpha added here. That's just the step size. So if we have a very large alpha, we say, oh, I see what this direction is, and I'm going to step really, really far in that direction. So if I have an alpha of maybe 1,000, I'll step really, really far in this direction. And I guess this is drawn wrong. It would actually be like right here. That would be the gradient. So we would step really, really far in this direction, like over here, and it would land us in some spot. You usually don't want a high alpha. If you have high curvature in your space, it could like kill your model. Like say I have a direction pointing here, in that direction, and let's say I have a really, really high alpha. What if I step like all the way over here? There could be like a really high loss value here, and my model is just complete garbage. It got worse. So we want to have a small alpha to kind of slowly step in the direction. If we look at the actual loss landscape of things, it's disgusting. You have like this jaggedy mess of something you don't want to or something that's difficult to optimize. It doesn't look nice like this parabola here. So you want to make a small step size so that you don't accidentally kill your model, and so that you're actually stepping towards the minimum. So we usually say, what is the direction of, or what is the gradient? And we set this value to be, I don't know, 0.0001 in the case of like GPT models. You set it to be really, really low. So,
Is
Is that the learning rate in LLM too?
Yeah, so this is the learning rate right here, and so for LLMs, there's a few more things you add to this, which we may get to in the end, depending on how much time there is, and I could always talk about it later. But yeah, this is the idea. You see a gradient direction, and you only step in it. You only step in that direction a little bit.
And that's how you update your weight.
Mhm, yeah. Yeah, so each step, it would probably be better to index these. So this is W at time t, and this is W at time t plus 1, and this is the gradient at time t. And alpha is a global alpha. I'm not going to change it. So basically your weights at some time step, so wherever it currently is updated to the next one by just stepping in the direction of the gradient, and that's all you're doing. So you do this for all of your data. And the way you do that is by finding the gradient with respect to all of your data. So global or gradient descent, I guess in the original sense, is if we have 4 data points, we're going to find the derivative, it would be the average derivative over all of your data here. So let's write out the equation for that. Actually, so what is our L? Our L up here, I don't remember the exact formula, but it's basically going to be the derivative with respect to all your data. Yeah. The derivative is a mess here, so I'm not going to write it out.
It's like Jacobian.
So you usually use the Jacobian to optimize it. This, again, has a closed form solution, so you don't need the Jacobian. I mean, we can look it up real quick.
For linear regression?
For MSE specifically. I don't remember it off the top of my head, so yeah. There we go. Here's the gradient. This is a really good image. Fantastic. Yeah, I mean, basically, you have the squared term, so you bring the 2 out in front, and you have, yeah, I mean, the gradient would give you, yeah. I mean, you can get it real quick by, if you do a little derivation, but yeah, basically, you want to step in that direction, and you can calculate the gradient. There becomes a point where it just doesn't even matter, like, what the derivative is, because you're using this massive chain rule. So, and since you're using this massive chain rule mess, the derivative doesn't really matter. As long as you have a derivative that you can take, which you pretty much can always take a derivative, then that's all you need. So basically, you take this derivative and you take a sum over all your data, or over all the data. So take a step in the direction of the minimum. That's what you're doing. Cool. Does that make sense? Nice. All right. I think. What? Sauce. All right, so so this basically gives us a line or a plane in some space. So all this is doing is optimizing the equation y hat is equal to wx without the b, where x is going to be our d-dimensional data, w is going to be our d by 1 dimensional matrix, and this is going to be our output, which is just 1. So if we add a batch size to this, which is our n up here, so n, we can turn this equation into this. So our output, we'll have n outputs. In this case, it was 4 data points up here. So n will be 4, and this will be, I have the matrix wrong. This will be an n by d matrix, and this will be a d matrix. N by d. I'm going to flip that. No, that's d by d. X and w. There. So this will be n, this will be d, and this will be d by d. Yes. Yeah, so this is how you would basically add, yeah, that'll be 1. Yeah, d by 1. So this is basically how you would model it for all data. So for all data in your data set, so for all n data points, you would have this equation here, where x is going to be a vector, or rather a matrix, where you have n rows, so n rows here, which are all d-dimensional. So d is the number of, basically, like in the first example, we had house size, and then we had number of bathrooms. So it would be all those variables, and that's just for every data point you have. So for every y, you have this set of variables, and then w is going to be your vector here, your weight vector that you're optimizing, and you basically multiply that by every input, and you'll get an n-dimensional output here. There, which is just your output for every single observation you have. This is how you generalize it to multiple inputs, so multiple examples that you have. So, this is just adding more data points. So you can increase n arbitrarily, and same thing. Now, what if we want to optimize this such that we add a nonlinearity? Like, what if we have data that's not nonlinear? What if we have data that looks like this? If you draw a line through here, it's going to suck. It's going to be bad. So this is where like the linear regression part breaks down, and you don't get any closed form solutions because you can't draw a line, and math doesn't do too well whenever you don't have linearity. It starts to become ugly. So let's start adding some nonlinearities in here. Wouldn't it be much better if I could, I don't know, let's go with a simple case. What if I had data that looked like this? So if I had data that looked like this is following a sigmoidal trend. You would want to add a nonlinearity to this so that it follows this trend. If we added a line, it would suck. But if we add a nonlinearity to it, we can basically model this nonlinear data. So in the simple case, the way we can do that is by saying, okay, so we have our y's, or our predictions, and what we're going to do is we're going to take the sigmoid of this. So sigmoid is just equal to 1 over 1 plus e to the negative x. And in this case, it would be negative y. We'll call it a, negative a. So sigmoid of xw here. So this will allow us to model nonlinear data that follows the sigmoidal trend. And the idea behind the optimization,
What's the point of sigma?
this is what they used originally. They say it's biologically equivalent to a neuron. So originally they're like, oh, so we have a step function, and you have data, or you have a neuron, and it's receiving a bunch of inputs, and the neuron spikes at some point. So then it spikes given a threshold. But then they're like, oh, we can't optimize this. We have to, because you can't optimize a step function. If we have a step function, it's very, what would it be? It would be, well, yeah, there's a discontinuity. It would be like if x is greater than 0, then you have a value of maybe 1. And if x is less than or equal to 0, then you have a value of maybe 0. And you can't take the derivative of this. Like, you can't, it's discontinuous. So what you can do is you can say, oh, I'm going to draw a sigmoid, which is this function here. That'll be Rx. And there we go. This is obviously a biological neuron. You receive inputs, and it gives you an output. This is a biological neuron. I don't care what y'all say. Biological. Yeah, so anyways, this is obviously not a biological neuron, but the sigmoid originally came from that. So then they can differentiate it, and they can do things with it because they can differentiate it. But yeah, sigmoid, I mean, you can see a sigmoid trend, but it actually sucks. You don't use sigmoid in reality. You use ReLU, but it's good to, I don't know, I like using it as an example. So the way you would optimize this is we need to get DL over DW to optimize this thing. And the way you do that is via the chain rule. You can't just get W, but the way we do that is we say, all right, we're going to use chain rule. So chain rule will allow us to basically, well, if y'all know calculus, it allows us to take the derivative of every function, and basically, if you know the derivative of sigmoid, and you know the derivative of our function here, then you can easily just chain these simple derivatives to get this really complicated derivative. I actually have a calculator which calculates derivatives, and if you look at the entire form of like the derivatives of a neural network, there's literally no reason to calculate it. So you can get this derivative in one equation, but it's best if you split it up into small equations, and it'll allow you to kind of checkpoint your derivatives, which whenever we get to really large networks, I'll mention that. But basically you take dl over dy hat times dy hat with respect to the sigmoid function times d sigmoid over dw, and this is equal to dl over dw. And basically you have this output, or you have this chain that you're modeling, which goes through every single function. This is easy to take the derivative of. xw is easy to take the derivative of. That's just w. Or with respect to x, that would be w, and with respect to w, that would be x. And y is easy to take the derivative of. Y hat is just, well, actually that's just the derivative of the loss function with respect to y. So these are all easy derivatives to take, and you just multiply them together and you get your derivative here, which is your entire derivative for w. So this is what backpropagation does. Basically, you are given this disgusting looking equation, which you can just start stacking, and all you do is you take the derivatives with respect to every function. So the idea is we take the derivative of, so L is a function of y hat. Basically, you just take the derivative of every function and you just chain them together, and you get your function here, or you get your derivative here. So basically, the idea is you just need to get your derivative somehow, and you do that by a chain rule. How do you implement that? I'll show you in code a little later here. But yeah, it's basically just chaining these derivatives. So let's build up a neural network. So the idea here is basically the thing we've created is we have y hat is equal to some nonlinearity of xw, where x is going to be a vector is going to be a matrix n by d. W is going to be a d-dimensional or d by 1 dimensional matrix. Sigmoid is just some function you throw on top of that, and y hat is going to be n-dimensional. Now what we can do is we can add an extra dimension to this, and let's say, well, what if I don't just want to model the house price? What if I also want to model, I don't know, what's a good thing to model? Something else. Maybe how many people are going to live in there or something. Something else. But so the way we can do that is we can say, all right, so we have x, that's n by d, but what if we increase w so that we now have two outputs? So if we multiply these together, we would get an n by 2 output. So instead of y being one label for every input, you now have two labels for your input. And basically this is drawing two graphs. You would have one graph, which is saying this is y1, and you have a bunch of input variables x. So in the one-dimensional case, you would have a line here, or a sigmoid, depending on what nonlinearity you use. And here would be y2, and this would be x1 and some other x's, and you now have the second output. Now if we generalize this, what if we say, all right, I'm going to add more outputs. So I'm going to say, I don't know, what m outputs here. So now what we have is we have n data points, which have n different labels each. So this is very arbitrary now. It used to be we have n data points where we have a set of inputs, basically modeling some house data, and the output is the price. And then we went to 2, which is maybe the price and the number of people living in there. But now we have m arbitrary values, and maybe you have a case where you have like 100 of these, I don't know. But the reason we're generalizing this is so that we can build a neural network with this. One last thing to generalize is this nonlinearity. So this nonlinearity, I'm using sigma in this case, can be anything you want. And what is usually used as your nonlinearity is something called ReLU or SciLU. But it's basically any way to add nonlinearity to your data. And ReLU is just the max between 0 and x. So ReLU of x is equal to the max between 0 and x. So this is the generalized form of our linear regression model. You can basically have a linear regression model with a nonlinearity output and basically have m outputs instead of just one. So this is the generalized form of our linear regression model. Now, to build a neural network, you basically just stack these things like crazy. So what we do is we have this generalized linear regression model, and we're going to generalize it even further by just adding layers. So this here is going to be one layer, and the layer you can think of as a weight matrix, so W, this linear function, and then a nonlinearity after that linear function. And that'll be what we're calling one layer. So let's start stacking these. So what if we had two layers? What if we say we have sigmoid 1, or some nonlinearity 1. Actually, I'll build this from the inside out. So let's start with our original function here. So this is our original nonlinear function. X is n by d. We'll say W is going to be d by d. Just for now, we'll say this is d by d. So this is one layer. This is what we had before. Now what we can do is we can say, all right, so we see that our output is going to be of shape d here, n by d. So we can add another layer that basically takes this and projects it to another space, or projects it via another W. So we add a linear function on top of our nonlinear data. You can think of this as basically extracting features from our data, and we're going to add a linear function on top of that that basically is modeling the extracted features from our original data. So this here firstly extracts those features. Now let's add another weight matrix, which is going to model the extracted features. And what we can do is we can throw nonlinearity on top of that as well. So this is a 2-layer neural network here, and the way you can visualize that is usually by this connection of neurons. So you have your d-dimensional input, and you have one layer. Our one layer, well, actually let's call this something else. Let's call this, and by d we'll call this maybe e. Yeah, we'll call it e by e, or d by e. So it takes our input here, x, and it projects it to an e-dimensional space. And what you usually see is you see these connected neurons, where this neuron is going to be the first linear function we have, which looks at all the inputs, all the data in your original, basically all the data in your original, all your features. So this would be like number of bedrooms and stuff like that, the square footage. But also you have another neuron, which is another linear function that does the same thing. It looks at the exact same data, but it's probably extracting different features. And you have a total of e of these neurons. And then what you do is you send this through a nonlinear function here, which then gives you some output, which is of the same shape, but it's just adding this nonlinearity. So each of these is a linear function, and you throw them through a maybe ReLU all by themselves. So then what we do, this is going to be e. Then what we do is we throw this through the second layer. So this here is our W1. W1 is this fully connected matrix that you're optimizing. It's our d by e dimensional matrix. Maybe we'll call this e by 1. Maybe we're just trying to get one feature from our data in the end. So we have this e dimensional vector here, which is a vector of e features from our input data. We then have another matrix here, which is just one neuron in this case, because we have a matrix that's e by 1. So this is one neuron extracting features from the features we extracted. And what this does is it looks at every part of this e-dimensional vector, looking at every feature, multiplying it by a weight here, and extracting one feature from that data. So this is going to be W2. And we throw this through an activation here, and this will give us our final output here, which is y hat. So this is a 2-layer neural network. We have one layer extracting features from our original input. We have a nonlinearity after that, which is making these nonlinear features. We have a second layer extracting one feature from our set of features that we extracted, and another nonlinearity to process that to add some nonlinearity to this. So this is a 2-layer neural network, and you can abstract this pretty much infinitely. You can make the networks wider by increasing e here, and you can add more and more layers by just adding more w's and adding more nonlinearities. And the trick is, as long as your input, so x here, which is say d-dimensional, and your output here, which is say 1-dimensional, as long as the shapes align, then you're all good and you have a neural network that should work. Yeah, what? It should work. So yeah, so this is basically how you make your neural network, how you scale it a bunch. Now, the way we do backprop is we take the derivative of our loss function. So we get our output here. We have our loss function here, which takes our y hat. And you're going to take the derivative of the loss function with respect to all the weights. Remember, we're trying to optimize the weights, or we're trying to find the best function that fits some data. And we're trying to do that by optimizing our weights here. So what we do is we take the derivative of the loss function with respect to every weight. So we will take, we'll optimize W2 by W2 is equal to W2 minus alpha times DL over dW2. And we'll do the same for W1. So W1 is equal to W1 minus alpha DL over dW1. And you may notice that W1 is back here. So the way you get DL over dW1, if we look at this function right here, so DL over dW1, you would do that by chaining DL over dy hat, this is y hat times dy hat over d sigmoid 2, I should label that, times d sigmoid 2 over d, that would be d, well, if we assign this as a, if we label this part here as a, and it would be d sigmoid 1, dA, and then you would do dA over d sigmoid 2, and finally, since you're in d sigmoid 2 over dw2. And basically what you're doing is you're saying we start here because this is the output of our neural network, and we're just going to move backward, which is where the name backpropagation comes from. So you can basically take the gradient and slowly pass it back through your network. And this allows you to not have to, you don't need to know what this function is, you just have to know what each of these individual functions are. So we have some gradient here, and what you can do, like this, the gradient here is just this gradient here. And what you can do is you can pass it back one layer by just adding this chain rule here. So now we have this gradient here, and since we're defining this at x, this is just going to be some matrix. You're just doing matrix multiplications on the way back by the gradient formulas. So all you're doing is go back layer by layer. So.
So why would you need to take, I understand the partial L, partial y hat, partial sigmoid 2, but why would you have to then take partial sigmoid 1, partial A? Could you not just take partial sigmoid 2, partial W2?
Yeah, it's just another way to break it up. Like this right here is equivalent to partial sigmoid 2, oh wait, that's partial sigmoid 1. Yeah, there we go, yeah. So this is equivalent to partial sigmoid 2 over partial sigmoid 1. It depends on like what your function is. So in the case,
and would that be W1 instead?
Yeah, this would be W1 here. So
Okay.
this would be, yeah, this is W1 right here.
Okay, that makes more sense.
Yeah, sorry, I mislabeled the indices. I was thinking right to left. Yeah, so this is what you would have here. Basically just breaking up your functions into small functions that are really easy to calculate the derivative for. Because if you wanted to, you could literally get the derivative for this, and it would be one function. It would just, it would end up just being chain rule, though. It's just easier if you do the chain rule piece by piece, and it saves a lot of memory and time. Because if you think about this gradient right here, this first one here, this gradient here can be reused, this one. This gradient, this chain rule gradient is needed for both W2 and W1. Mm-hmm. So you can save memory and time by just calculating this gradient here, and then passing that to W2 and X2, or to A. And then W2 is updated, but then you have to keep that gradient and move it backward to W1. So this is why you're doing backprop instead of just calculating the entire gradient formula for every single W. So you could if you wanted to, but you don't do that if you want to be efficient.
Question for you. So to go all the way back to the beginning, so when you were talking about how you got your new data point, you're going to find the descent, whatnot. So once you have that descent, is that the equivalent of if you just ran the linear regression again, but you added that latest data point to the data set? So would the resulting linear regression there be the exact same as if you applied the descent on the old regression line?
So like if I have my regression line here. I have my data here, and I have this, my line here. So this is a y hat, which is equivalent to, it has WT, and then I apply descent one time, but I take the data points from the line itself. So this has a bunch of predictions here. You're saying I take the predictions it has and plug them back into the data set?
Well, what I was saying is, so for the very first one that we compared it against,
Yeah.
right? So seeing how far off we were.
So like this one here.
Right, and if we wanted to adjust our model, would the magnitude of that adjustment basically be the same as if you added that one data point into the model and then did the linear regression again?
So the way you get this residual is by doing the linear regression with that. And the way you update it is by looking at not just this residual, but every single residual at the same time. And you adjust it based off the average magnitude, the MSE, so the average magnitude, and you take the gradient with respect to the average residual. So the gradient you have is not a direction to update the model for just this one residual. It's for all the residuals.
Right. So I guess what I'm wondering is, if you had just added that data point to the data set and ran the linear regression again, would that change be less than or equal to the change if the descent?
Oh, so it would change it just for, so it would be a different change. It's a different direction. So if we just were optimizing that, you would get a model that probably looks like this. So because it doesn't care about the other data points. It's not in the gradient. The direction of the gradient basically informs it. This is how you update with respect to the average, or this is how you update for the average data point. But this basically says, this is how you update for this one data point. So just optimize that one data point.
Okay. Yeah, I think we may be talking about different things.
Oh, wait, what? So,
Basically, the idea is, hey, if this data doesn't fit super well, just add the data to the training set. Now what do you get? What's
Well,
the difference between both?
all this is in the training set.
Oh, okay.
Yeah, this itself is the training set. The tests, so yeah, this is all your training data, and you're trying to optimize the model on that.
Gotcha.
So this is what we're calling the training data. Yeah.
Sorry if that didn't make sense to anybody else. It didn't make sense to me for a while. But
Oh, well, so like I guess you have
no, I
like
think
are you talking? Oh,
I
good.
think we're good now.
All right, cool.
Now that I think about it, now that you explained it, it makes more sense. But if that was a dumb question, I apologize.
No dumb questions. So, yeah. So does the neural network idea kind of make sense to everybody, and how you kind of do this chain rule to get your gradients, and like you do what you did before with the normal linear regression. You just take a step you take a step towards the minimum, and you keep on doing that. It's just you have a lot more parameters you're doing that for now, and you have this multivariable thing. But this is still in the end just a function where you have your input. So if we have x is equal to 1 or d is equal to 1, then this is still just a line like we had here, where your input is just 1 and your output is one dimension. So the space is the same. It's how the input-output space is the same. It's how you're modeling it via these intermediates here, which are features of features. So in the end, you would still end up with this line x versus y, or many x's versus y, which would be a plane. It's just a lot more curvy now. Like if all of these were sigmoids, or if all of these were ReLUs, you would get some really weird curve. It wouldn't be a line anymore. So now you can actually model things that are useful, unlike a line, which usually isn't that useful. So yeah, that's the basic idea of linear regression, or linear regression and MLPs, and kind of optimization. And you can make this a little bit better, which I don't think we will get to today. So should we talk about CNNs next?
We have that now, right?
Yeah.
That's a good segment.
Anything I missed?
So when the network also gets deeper, right, and you start doing the background, as you change those, like, the product of those gradients, the gradients get smaller and smaller and smaller. So there are techniques so that when you start optimizing the network, the deeper it is, so that the front of the network also get optimized. But if you leave it like this, like the middle, the deeper you go, the deeper the network is, the harder it is to make it better. That makes sense?
Yeah. So that's a really good point. The derivatives are being taken from right to left, so the loss, and you keep on multiplying over and over and over again. And if you think about like multiplications, and you're doing these dot products, you are going to get what's called exploding and vanishing gradients, where either the gradient will get really small or the gradient will get really large. And like the gradient itself is valid, it's just we can't handle that precision whenever we're dealing with computers. So he mentioned like there are ways to get around this. One such way is residual connections, but
The term residual will come.
residual comes into play again. It's just a word. That's all. Residual connections, basically what you can do is you can have the model, instead of taking all the data and using that data itself as the feature, basically changing the data over and over and over again, you can basically have the model say it has a layer, and the layer is going to be used to inform how do you kind of update the original data. So you have a set of original data, and you're going to update that part.
I think it's better if you draw it out.
Yeah, I'm going to draw it out. So basically the idea is you have your input vector x, which is d-dimensional, and you have, say, a layer here. So this will be your layer w, and you have your output. Maybe we'll call this a. So this will be sent through the layer, and a is going to be equal to a nonlinearity of x times w. And what you do is you add the input x here. And what this is saying is instead of So if we just had this part here, this is saying our features are going to be the extracted features from X. So our features A are going to just be what we extracted from X. But if we add this residual here, it's basically saying this is the change we want to make to our original data to kind of basically maybe you can completely change it and I don't know, you get some new set of features, but it's a way of also just having gradients flow. That's what people say, and it's a way of getting rid of this vanishing or exploding gradients. And if you write out the gradient formula, you would see why. Basically, if we take the gradient with respect to A, or if we take the gradient of A with respect to X, if we just have, if we don't have this part here, if we just have this, basically we have to go through this multiplication with W and through this nonlinearity, and you basically have to go through 2 layers. And let's say this nonlinearity was ReLU. Let's say it was ReLU. So this is what ReLU looks like, the max between 0 and X. And what this does is it basically says the gradient is equal to 0 if you have a value less than 0, and 1 if you have a value greater than 0. So if we take this gradient with respect to X, and let's say we have a lot of negative values for X times W, the gradient is going to give us almost all zeros. So then any layers before that will get a gradient value of 0, meaning they're not going to update at all. But if you instead add X here, the gradient with respect to X, or the gradient of A with respect to X is equivalent to this mess here, but also just to itself, just to one. So you still get this gradient flow, and that's the idea behind residual connections. This is how you can make, this is a really big technique for making the networks really, really deep. If you play with this code, you can't make it deep at all. So actually, yeah, I'll go ahead and go through the code now. So code. What? Yeah, code. So I'll send this out. It is a really bad, it's bad. I did like a speed run of neural network, but yeah, let's go through this. So the idea, let me turn this off.
Has anyone written Torch code before?
No, this isn't Torch.
This
It just said torch at the top.
Well, it's not using Torch.
Import
It
torch.
could just be NumPy.
It's NumPy.
Okay.
Well, so it uses Torch tensors. It's just a tensor though. I use it so that I can throw it on my GPU. Yeah, no, the idea is to implement it from scratch. Yeah.
You could very
Yeah.
well just replace Torch with NumPy, and it would probably work.
You can't put that on the GPU though.
I mean, you could put it on the CPU. No, I mean like your code would still run.
Maybe.
It
I
would
mean,
run
you'll probably
You're
walk.
training on MNIST, so it'll probably still run.
Yeah.
I think it'll run.
Let's just be real.
Overclocking my good man.
Yes. Who needs GPUs when you can get like 1 million overclocked CPUs? Yes. All right. So, anyways, I'll just go through this. It's like a really simple neural network. I import Torch just so that I can put it on the GPU. But yeah, I'm using NumPy. So if you've ever seen NumPy before, this is what it is. But NumPy is just a way of creating matrices and working with those. The ampersand sign is dot product. So whenever we were talking about X times W, that's just dot product, inner product between X and W. So let me zoom in a little bit.
I import Torch just so I can put it on my resume.
Yes, y'all have seen Torch. Put it on your resume now. If y'all don't have it, throw it on there. So yeah, linear layer. Basically, all you need to do is create a weight matrix and a bias. This can be removed. I hate bias. So you just initialize this weight matrix. And I said this is a D by D matrix. So this is your input dimension, and this is your output dimension, D in and D out. And this is just an initialization strategy. Basically, it's so that the gradient isn't disgusting. If you initialize it too small, you're going to get vanishing gradients. If you initialize it too large, you're going to get exploding. This is a empirical formula that people have found. Empirical comes up a lot in machine learning. So the forward method is just as shown earlier. It's X times W plus B. The backward method, so basically at every layer, you need a forward and backward method. And what the forward method is going to do is it's going to say, it's just the function. It's the function itself. And what I'm doing here is I'm taking the input into the function so I can use it in the backward process as well. And the backward process is going to take the function. It's going to take the gradient from the past layers, or from the layers up to the loss function. So the loss with respect to all the things before it. So maybe that was like dl over d sigma 1, so something like that. So it's taking these previous gradients. Maybe this is like dl over d sigma 1. So nonlinearity, basically the layer after it, the layer to the right of it. This is that gradient, and we're going to multiply it by d sigma 1 by dx. And this would give you, the gradient dl over dx. Or if we do this in terms of w, it would give you dl over dw. So this here is doing all that. So the weight gradient here is just the transpose of the input x. It just is. Yeah. The bias gradient is just it's just the previous gradient, just the sum. So this here, I'm clipping things for exploding gradients. I don't have any residuals because I didn't feel like making a gradient for that. So this is our update function here. The weight at time step t plus 1 is equal to the, this is just subtracting the gradient. So this is the direction of steepest ascent. I'm subtracting it, so steepest descent, and this is just the learning rate. This is the formula I showed earlier. This is the same. It does that. And this is basically updating our x gradient, which is going to allow us to send the chain rule gradient to layers before it. So that's all this function is doing.
Does it make sense?
Yeah. Does it? If not, let me know.
It's making more sense than when I started, so.
Like, that's good. Yes, I'm not making it more confusing. Let's go.
If not, I have a really good YouTube video for you. So.
Yeah, we're gonna send out some resources. This is a quick rundown of everything. So then this is your activation. You also need to have, this is just our activation function, which is the same idea. You have forward and backward here. So forward is just throwing it through the activation function. Backward is just throwing it through the is taking the gradient of that, and I have all the derivatives here. And then chain row right here. And you mentioned the Jacobian earlier, so you do actually need to take the Jacobian if you always take the Jacobian, but you can simplify it if there are no dependencies between, You always take the Jacobian, but you can simplify it if there are no dependencies between your, for example, if I take ReLU, there are no relationships between the variables, so you just take the, I think it's just the diagonal of the Jacobian. Which gives you, so you don't need to take the entire Jacobian.
It's just x, x, y, y, z, z.
Yeah. So, but you do for like softmax, you need to take the Jacobian, and you get this awful matrix that you have to use. So let's make a neural network. This here is our input, so 784 by 1024. This 784 is our input dimension. This is our first hidden dimension, 1024. So this is just one layer. This is a weight multiplication, and this is our activation. So this right here is Wx. This right here is sigma of Wx. This right here, Wx. This is going to be this is going to be sigma of Wx, and then you multiply by W again. W should be on the other side.
What's the significance of 784 and 1024?
So 784 is 1024 is arbitrary. I just feel like picking a power of 2. 784 is going to be our input dimension. So I'm using MNIST. It's just a data set. I just flattened it, and that's just our input data.
28 by 28 images.
Yeah, 28 by 28 images.
That's what I'm saying.
And then here, so we have two layers. One layer is going to have 1024 neurons. The second layer is going to have 256, and the output is going to have 10 classes that it's classifying from. So MNIST is just this thing, MNIST, here. Basically, given some digits, classify them.
This is like the hello world.
Yeah, this is the hello world of machine learning. So forward just iterates through every layer and just sends the input from one layer to the next layer. And output here, this here is updating the model, the backward method. And all it does is it takes the labels. So the label is going to be 0, 1, 2, 3 up to 10. And it basically calculates this loss. It's not mean squared error loss. I'm not going to get into the loss, but the loss is just saying it's another loss function. It's not cross entropy. It's negative log likelihood. It's basically matching distributions. It's the same idea with mean squared error. It's minimizing the residual, except with distributions. It's minimizing the difference between distributions.
Just keep in mind that big loss,
Yeah.
small loss,
But yeah, we don't want big loss. So just this calculates the gradient. I mean, it's disgusting. No need to look at it. And then this is propagating the gradient backward. So we have this gradient with respect to the loss. This is dl over d like y hat, what I showed before, and we're propagating this backward. So for the first layer, we have dl over d y hat, and then it's going to multiply that with dy hat by, it would be d sigma, I think 3. I think there were 3 nonlinearities. And then it would keep on multiplying this. So the first activation would give you dl by dy hat times dy hat by d sigma 3, and then times d sigma 3 by dx3. And then you keep on doing this over and over and over again, but every time it does a backward step, it updates that layer as well. So for the first layer, it would be this layer here. So it would send the loss gradient to this linear layer. And if we go to the backward process here, it'll take the previous gradient, and it calculates the weight gradient and the bias gradient. It does the update for that layer, and then it returns this gradient, which is going to be dl over dy hat, which is previous gradient, times dy hat over dx, and it returns that. So once it returns that, we then take that gradient and we pass it to the next layer. And the next layer is going to be an activation. There are no weights in the activation, so all it does is it takes this gradient, it multiplies that gradient by the gradient of the activation, and then it keeps on passing this backward. And as we're passing things backward, it updates the model so for every layer. And this is where you see the chain rule happening. It's just a chain rule for every step. And to train this thing, basically what you do is you iterate over the data a ton of times, and you're just feeding in a ton of data. You're saying, what's the loss? Update the model according to that loss. And you just do that over and over and over and over and over again. So that's all you're doing here. It's not. If there are any questions, let me know. Yeah, I'm running it. Do you think it's not going to work? I test well, it theoretically should run, at least. Yeah. It's going to blow up? I believe. I'm not outputting the intermediate steps, and OBS is open. Maybe I should close that. OBS, get out of here. Let's go, 90%, yes. That's not good on MNIST. It's better than 9%, that's for sure. So basically the way you would make this better is you would just add more and more layers, but you can do this using something called AutoGrad. And AutoGrad is an amazing thing where it does all of this for you, and you don't have to do any of it, because this is a pain to do the forward and backward process.
AutoGrad stands for automatic.
Yeah, basically it does exactly what we have here, which is just the forward method.
Backwards code. That's AutoGrad kind of fills that in for you.
Yeah, but it does exactly what's happening here pretty much. It takes the gradient and passes it backward for every layer. It just does it in a much smarter and more efficient way than this. It works. It does the thing.
You know, somebody coded that neural network in Minecraft.
Oh yeah, it was Yannick. Yes, I love Yannick. Or Yannick, yeah. What do you mean? This network's super powerful. I don't know what you're talking about. Yeah, I mean, it does the thing. So yeah, that's the code. Now real quick, we can go over CNNs. So we'll go over CNNs real quick, just one last thing, which is just another neural network type. The next time we meet, we'll go over transformers and RNNs, which is the basis of a lot of other things. But just to kind of have it out there, we'll go over CNNs. So the idea that we have now is we have this input vector, but what if we have like some more structured data? What if we have, say, an image that we want to process? So the basic idea of a CNN, we have this image here.
Hey, do you want to be recording again?
Oh, it's recording, just not, it wasn't recording on OBS.
Oh.
Yeah, so the problem is I have an HDMI cable and it wouldn't let me broadcast. And since I have an HDMI cable, I can't do OBS, so I'm recording on my on my tablet, which is better than nothing, hopefully. But yeah, people won't see the code if I was recording, but thank you, yeah. So the idea here is, let's say we have an image. The last time I drew a dog, it was like high. You know, I'll draw a dog. Oh man. You- I'm not.
Start by saying, remember guys, I'm not an artist.
Remember, guys, I'm an artist. Yeah, you're right. It can be a pig.
I see dogs.
It's stone
Be a
now.
dog that looks like a jackal.
It's stone.
Remember, I'm an artist.
Just not a good one.
Trust me, I'm really good at art. I don't know what you're talking about.
Dog looks severely bloodshot.
It may be on some drugs, but so yeah, we have this image, and let's represent this as values instead, because that's hard to look at.
Garbage in, garbage out.
No. This is a masterpiece. So if you put this in, it'll give you a good output.
So is it an NFT?
What's the link to your Patreon?
I'll send it to you personally. I got you. You can have more of this amazing this mess. So anyways, convolution. So the idea with the convolution is instead of having, so we have this input, and we have this input that's like an image, or we'll go with images for now, but you can change the kernel size and stuff, but we'll go with images. And the problem with an image, it is very massive. Like here, it's not that massive, but MNIST, we already had 784 values, and it was just a 28 by 28 image. But imagine we have an image that's 1024 by 1024. We're gonna get a lot of values. I don't know, how much is that? Like 1 million? I think that's 1 million or something.
Yeah, like 1 million.
Yeah.
So, sorry, give it like.
1 gigabyte, but yeah, that's a lot. So 1024 by 1024 image gets, you start getting a ton of features in your input space, and you can't work with that at all. It's just impossible. And also, the neural network is not going to find relationships that you would see with like, the idea behind a convolution is it's a lot more, I don't know, vision-y, a lot more, yeah. It finds it's going to extract filters, so talk about kind of the filter.
So basically, we want to maintain the structure of an image as it goes through. So in the previous example, when we were talking about the NLP, we had a 28 by 28 image, right? But to feed it to the network, we have to flatten it into a 784.
Yeah, 784.
All the structure is gone. But
Yeah.
it works because the image is simple. So when you get to more advanced territory, you want to maintain that structure as much as possible to give a chance to the network to learn that structure, even better.
Yeah, so if we basically flatten this to a vector here, like you said, you lose all the structure. This here is independent of this here. There's no relationship between how close they are. Once you, like, they're close on the paper or on the tablet, but they're not close. These are just two values. They're two independent orthogonal directions that you're working with. Here, though, if we work with an image itself, you have that structure, like he was saying. You know that this pixel here and this pixel here are close to this pixel here. But here, you would have, this one would be the 1, and this one would be the 0. So yeah, you run into this issue. Yeah, so what we're going to do is we're going to use something called a convolution, and a convolution is basically a sliding window. It's a filter that you're using. So this is going to be our W, and our W is going to process this input image by using a sliding window. And the way it does that is you do a dot product between these, but you slide it across the image. So you don't do it via, you do it via one dot product, but I'm not going to get into actually how you implement this. Basically, you're going to do the dot product over every sliding window part. So basically, we can take this here. So this is a 3x3 filter, and this is a 4x4 image. We can take the filter here, and we can put it on this first 3x3 part here. I don't know, maybe this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm gonna regret doing this. 1, 2, 3. 1, 2, 3. There we go. Let's say this is our filter here. So what we can do is we can multiply every single one of these values by every single one of these values and add them up, so just dot product. And this will give us an output, which is a single value. So we do 1 times 1, so it'd be this one times this one, plus 2 times 0, plus 3 times 1, and so on for every single value in this filter, if y'all see how I'm kind of applying it to that. So it's just inner product on these two things, and this would give you a value, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would give you a value of 10. And then what we do is we move it over 1 pixel. So we now have a filter, which is going to be right here. Or we move the filter over 1 pixel. And what this is going to do is we're going to multiply the same exact filter, except it's on a slightly moved over part of the image. So we would get a value here, which would be 2, 3, 4, 5, 6, 7, 8. That would be 8. Yes. So this would be a value of 8. Now, what this value here represents is it represents the top left part of this image. And what this second value represents is it doesn't represent an independent part of the image. It represents both the top part of the top left part, but slightly moved over one. So you have this overlap here. And this overlap is basically, it's important because these two output features are now, combinations of this input here. But it gives you this locality here. This filter is looking at features local to the image. So this filter here, it's looking at local features on a 3x3 grid. And you get this output here, which is going to be 2x2, we'll call this 7 or we'll call this 6. I don't know what the values actually are. But it basically, you slide, the next thing you would do is slide it down 1 here. This would give you, I'm going to say that's a value of 7. It may or may not be. And you would slide it over here and that would give you a value of, I'm calling it 6. I don't know if it is. And you get this output here, which represent the features, where 10 is represents the features from this here. 8 represents them from this upper right part here. And yeah, basically this is just extracting the features for 3x3 parts of your input image. And this is one kernel. So you have this kernel, and this kernel is just extracting features for 3x3 parts of your image.
So the W is
Yeah, the W is the kernel. So your weight matrix is going to be your kernel, and your kernel is extracting local features from your image data or whatever data you're processing. What we can do is we can say, all right, so this is extracting something. Maybe it's extracting edges from our data. There are edge detectors. You can define a 3x3 grid that does extract edges from your data. So the output would be edges of your data. So one filter extracts simple data. What if we add another filter? So let's say we add another W here. We'll add another W, which processes the exact same image here. So this will be W2. W2, this will be W1, and this will give you another 2x2 output. We'll say this is also 3x3. So it processes the exact same input, X, and it will give you another output. Maybe we'll call this Y1 and Y2. So we have our input image here. We have two kernels that are processing different features, and we have two sets of feature outputs. And this is what a convolution essentially does. It's just having this sliding window that goes over your entire image and extracts features out of it. So these filters are very basic. It extracts basic features from your input image. But now let's kind of abstract this to a neural network sense. So our input X here is going to be an image. And our first layer is going to be a set of convolutional kernels. So this is a set of 2 kernels, which gives us a set of 2 output images. So our X input is going to be a set of images. Maybe this is RGB images. And our first layer is going to be a convolutional layer, which is going to be represented by a bunch of filters here. So this will be number of filters, and we'll call this W. And our output here is going to be a set of outputs here, which is equivalent to the number of filters we have. So this is the number of filters. I don't think I spelled that right. Spelling issue. And this will be Y. So the idea is you have your input images here. This is going to be sum height by width by number of channels here. So you can think of this as height, width, RGB. So R, G, and B. Okay, whatever. That's a G. G and B. Your filters are going to process these, and I forgot to mention you can add depth to this. So if we add depth to our input X, you would add depth to every kernel. So this kernel here is actually, it has depth as well, so it would process the depth of your input X. you can add depth to it, but it's the exact same operation. So your output y, it would be the sum of the depth as well. So it can also handle that. But the idea is you have these filters, each independently process your input image x, and it each outputs a set of extracted features. So let's say these are edges. I don't know, maybe it extracts edges or something like that. So all these sliding windows process our input x, and it extracts a different feature. So this feature here, y, will correspond to this filter, this one will correspond to this filter, this one to this filter, and so on. So looking at this in a neural network sense, this is a single layer where this is our input x, this is our weight matrix, which is going to be of shape, I think that's, I'm forgetting what the shape is. It's some mess, it's some equation. It's like height by width over 2 or something like that. And then you have your output y, which I'll say is like lowercase h by lowercase w by your number of filters. It's something like height by width by number of input channels. So it'd be like 3, your number of input channels, by your number of filters. It's not exactly this. The way you do this is not, you don't do a sliding window, you actually unroll the entire matrix and you do a bunch of dot products. So the shape of this is weird, but something by 3 by the number of filters, which is the exact same thing as we had earlier, where this is your input dimension here, C, or 3, and your output dimension is the output dimension in the layer, so your extracted features. And you just stack these layers. So another layer, which is the number of filters, so you add another layer here, and your second layer would then process the extracted features from the first layer, and you just stack these. So instead of stacking multi-layer perceptron layers where you just have this W matrix, which is then being multiplied by your input, you're extracting these filters, which are these convolutions that go across your input and give you your output features. So these features would then be processed by another set of kernels, and you do this multiple times, and this gives you a convolutional neural network. So the idea is instead of using a weight matrix, you can use a weight matrix, which instead scans over your image. So it's just a different way, but it's still a weight matrix, and you learn the kernels instead of learning the weights in your weight matrix. You learn the kernels.
So it's like the weights are in the kernel.
Yeah, the weights themselves are these values here. You're learning these. It's the exact same thing as a weight matrix. It's just you have this sliding window, so it's learning these values. And you can think of like the first layer is learning the edges, and then the second layer is it's learning how to combine these edges. Maybe it can combine them to create curves, and then it takes those curves and maybe at the end of the network, one of the features is like a face, and it can find a face or something like that, or an eye or something. So as you stack these features, it processes features of features of features, and you get complicated feature outputs. So that's a convolutional neural network, kind of the gist of it. Yeah. Speedrun convolutional neural networks. So RNNs we'll go over next time with transformers, but yeah, we'll have a lot more time to go over that. This is just a speedrun basis of a ton of machine learning stuff, and we'll send out some resources on stuff to kind of look at. But yeah, anyone got any questions about any of this?
Make you feel confident? Like, I don't want to say confident.
More confident.
Like, do you feel like you got something out of it?
Cool. That's good. If not, go grab some chicken. Or if you did, or if you didn't, go grab some chicken, I guess. We have a lot.
Again, like,
What's this?
this one is there. If you feel like there's something you'd like to revisit, please make use of this one. Like, ask questions. Do a trial for us.
The guy who left early is from my lab, and I invited him to this. How can I share the recording with him?
We'll post it on YouTube.
Okay.
We post like all the recordings on the YouTube channel. Yeah, we'll also show the code.
Okay.
We'll send all the resources out in the announcements. Yeah. But hopefully y'all get hopefully y'all have like a kind of a basic understanding of like what is more of what's going on, not necessarily, oh, I want you to implement a neural network from scratch. More of what's going on, like, oh, how do the optimization procedures kind of like what are we doing with machine learning? Because like we're actually going to be going deep into what's going on for transformers, and without like a basic idea of what is optimization, what are we trying to do, it would be very hard to kind of go over that. So hopefully you'll have like just at least a basic idea of kind of what's going on. This was not meant to be thorough at all. we would be here all day. So hopefully y'all have like a kind of at least a better understanding of optimization and a kind of why are we doing the things, or like what's kind of being done under the hood. So yeah, and yeah, love to answer questions. But I'll also go ahead and stop the recording now. So.